Welcome everyone, and thank you very much once again for your patience. I am very happy to have Viktoria Kabel here today, who is a PhD student at the University of Vienna, working in the group of Czeslaw Brucker. And she's visiting here, as I already announced, for a few weeks. Unfortunately, not for much longer. She'll soon go back. And she's working on the combination, if I understand correctly, or how to involve space-time and causal structures into bringing into the fold of the foundations of quantum physics. And we're going to hear about that today, I assume. Quantum symmetries for spacetimes and superposition. Please, Viktoria.
Thank you for the introduction, and thanks to you all for coming and welcoming me in Geneva more generally. So the point of this talk is to give you an introduction into a bunch of research that has been going on in the past few years on quantum symmetries. And the idea of quantum symmetries is to take the classical symmetries and to generalize them to the quantum realm using the tools of quantum reference frames. And in particular, I want to talk about how we can use these to better understand the intersection between quantum physics and gravity, and in particular, spacetimes in superposition. And I want to start by I also want to stress that, of course, I didn't do all this work alone. This is based on joint work with many great people, most of them based in Vienna, which I'm very grateful to collaborate with. And I just want to start by motivating why we would be interested in quantum symmetry principles. And really, I'm just going to start by giving this quick introduction and then go into a bit more detail into the formalism. And for the first part of the talk, we're going to mainly be concerned with one particular quantum reference frame transformation, or quantum symmetry, for the translation group, just to get a grip on the formalism and the idea. And then in the second part of the talk, I want to generalize this and take this also to a more abstract and more conceptual level so that we can maybe understand the insights better without getting lost in the formalism. And in particular, I want to talk about the arguably maybe most general symmetry group that we might be interested in, of quantum diffeomorphisms, and what they tell us about the nature of spacetime in a quantum realm. And something that I would like to hear your opinion on and discuss with you further is whether we can make something like a quantum Hall argument using these quantum symmetries. So, why do we care about quantum symmetries? Well, they're useful already for studying very basic scenarios, like if we take a massive object and we put it into a superposition. Now, of course, we're not going to put the Earth into a superposition, but things are getting more hopeful that we might actually be able to create a massive superposition of something like a tiny gold sphere of maybe the Planck mass. So maybe in the next 10, 20 years, maybe a bit longer, physicists will be able to create such a superposition in the lab. But we still don't have a theory, or at least not one unique theory, that would describe what happens to, say, a test particle in the presence of such a superposition. This is a scenario that cannot be described by quantum mechanics or GR alone. We need to know what is the gravitational field sourced by a quantum object. Now, of course, you could take a particular stance on quantum gravity. If you take a high energy theory, it might actually be difficult to get concrete predictions for this scenario, but you could go other ways. Like you could argue that gravity has to be semi-classical, that we just see an average gravitational field and the particle will just fall towards the middle. You could go with Penrose's argument, argue we cannot really create such a superposition. It's going to collapse necessarily and the particle is going to fall either to the left or to the right. Or you could say, well, we actually do have a gravitational field in superposition and the particle is going to fall towards the mass in a superposition as well. But we're wondering, can we make an argument for the motion of the test particle that doesn't necessarily commit us to one such approach? And with quantum symmetry principles, we can do exactly that. Namely, these quantum symmetry principles allow us to change the perspective, to change the view on this problem, and to change into the reference frame of a quantum object. And then it's kind of like with classical reference frames. They're super useful in solving problems, right? If you want to know the motion of a ball when it falls down in a moving train, you're not going to describe everything with respect to the platform. You're going to jump into the frame of the train, solve the problem there, and because the equations of motion governing the ball are invariant under constant boosts, you can just go back and infer what happened with respect to the platform. And similarly, the idea is that with a quantum reference frame transformation, you can go into the reference frame of the Earth itself in its own reference, and I'm going to make this much more explicit in a bit. In its own reference frame, the Earth is going to look definite, and then we suddenly have a problem that we can solve with known physics, that we even have empirical data for. Like, this is just a classical gravitational field. We have a quantum particle is obviously going to fall in a superposition of paths towards the massive object. And we actually have experiments that test the behavior of neutrons moving in a superposition of paths in the gravitational field of the Earth. It's the so-called cow experiment. So we actually know that the particles will pick up a certain quantum phase in doing so. So we can solve the problem here, and then if we put in this one crucial assumption that of course has to be tested eventually, that the equations of motion are invariant not just under the classical reference frame changes, but under these quantum reference frame changes, then we can go back. We know the particle moves in a superposition here, so it's necessarily also going to be moving in a superposition in the original frame of reference. And we can do this entire argument without ever having to talk about the gravitational field on the left-hand side. So in this sense, these quantum symmetries can be seen as maybe a guiding principle to approach certain quantum gravity problems. But of course, this was very vague. How do we actually do such a quantum reference frame transformation? And this is what I want to introduce you to in the next 10-15 minutes. So when I speak about reference frames, I just want to make clear for the translation group, this can be really just seen as a choice of the 0 point of the coordinate system. So in classical physics, we often have a theory that's invariant under translations. It doesn't matter if I describe my bunch of particles over here or my bunch of particles over there, as long as there is no varying background field, the physics looks the same. And this invariance gives us a lot of freedom in the description. We can choose to describe everything from the point of view of one particle, the other. We can jump into the rest mass frame of the particles, and there is just this redundancy in the description that allows us to freely choose the position reference frame, to freely choose the 0 point in our description. And the idea is now that we take this to the quantum level. Imagine that instead of the definite particle here, we have a quantum object. So classically, the reference frame transformation is pretty obvious how to implement it. You just shift everything by the distance between the two reference frames, right? You just shift everything by XA so that the new reference frame ends up in the 0 point. And I'm mentioning this because this is something we want to retain if we go to the quantum level in the special case where we have quantum particles, but they're still very well localized around classical positions. So now we've basically done nothing except put cats around the states, but now we can describe everything in terms of quantum states. We're going to have these two physical situations, which we would argue are physically equivalent because of the translation symmetry, and they're generally described by two different quantum states. And in going to construct the quantum reference frame transformation, we can ask ourselves already at this level, what would the map look like that takes us from one description to the other? And generally, we want something like a unitary map that will act on the wave function. And it should be unitary because that way, automatically, all observable quantities are going to be invariant. The probabilities and the expectation values of observables stay invariant under unitary operations. And we also want to make sure that everything gets shifted in the right way. But that's still very easy at this point because in quantum mechanics, translations are just implemented by the momentum operator, or finite translations are implemented by the exponential of the momentum operator. And in particular, just want to mention this here, we have here the generator of translation, and we're just multiplying it by the amount that we shift our coordinate system. So this is for all the other particles that are not acting as reference frames in either of the two frames. For the reference frames themselves, at this point we could just shift them, but for technical reasons for later construction, it's actually easier to just exchange their positions, and this can be done with the so-called parity swap operator, which is a very fancy word for something that just changes the sign of XA and then changes the label of A and C. so that in the end the new reference frame is in the 0 point and the old reference frame has the mirrored position of it. So far really we're just doing some kind of quantum translation. But one thing that's already nice is that this actually also works if all the other particles are proper quantum particles. We can still apply the quantum translation operator. But it's still not like the most interesting situation. Like we're still changing between two basically classical reference frames. And when things really get interesting is when we consider jumping into a particle, so to speak, that is in a superposition with respect to the original reference frame. So how will we do that? Well, instead of just giving you the operator that does this transformation, let me try to motivate it a bit. Let us see what kind of things we want to retain from the classical reference frame transformations. So one thing that we definitely want to retain is that in its own reference frame, the particle is still at the 0 point. Like it doesn't really make so much sense for it to be in a superposition with respect to itself. So we're going to enforce that. The other thing that we want to retain is that the relative distances should stay the same. Like what really counts in a translationally invariant theory are the relative distances between the particle. And really when we speak of having a reference frame, what we mean is just expressing the positions of all the other particles as the relative distances to the reference particle. And we want to retain these relative distances. But now already one weird feature comes up because we've made this particle definite, but we still want the relative distance to be in a superposition. So we're going to have to put the other particles in a superposition. And the way we can achieve this is by doing a branch-dependent translation. We can say, oh, in the first branch of the superposition, I'm just going to shift everything by xa1. And in the second branch of the superposition, I'm going to shift everything by xa2. And this leads to the third interesting feature, that is that we actually end up with an entangled state. So we've gone from a non-entangled state to an entangled state, which maybe at first sounds a bit weird because you can't create entanglement out of nothing. But what the entanglement really encodes is just the fact that whenever the blue particle is closer to the orange one, it's further away from the gray one, and vice versa. In order to retain this, at this level of the description, we're going to make sure that whenever the blue particle is here, the gray particle is going to be over there, and vice versa. And this is why we have here an entangled state of the blue and the gray particle. And the way we can implement this quantum controlled translation, like translating differently in each branch, is by almost the same operator as before, except that we now promote the distance by which we translate to a quantum operator. So here's a hat on the distance xa. And what this does is it first reads out what is the distance xa from the new reference frame to the old one, and then translate everything accordingly. So what the quantum reference frame transformation does is it imposes a quantum controlled translation, different translation in each branch. So importantly, this also tells us already about what this quantum symmetry might look like. So as before, we can say that an invariance under a reference frame corresponds to an invariance under the change of reference frame corresponds to a particular symmetry of the translation group. Now we have the invariance under quantum reference frames, these quantum controlled translations. It would correspond to an invariance under superpositions of translations. And importantly, we've seen that this makes both superposition and entanglement a frame-dependent feature. And this, especially the frame dependence of the superposition, is also what allows us to now solve problems that we weren't able to solve before. So if we go back to the example of the massive object in superposition, and we want to describe the motion of a test particle in its presence, we now have a very simple strategy. In fact, the problem depicted here is basically like the problem with the three particles, where the Earth is now the orange particle, the new reference frame that we want to jump into. And I'm just not depicting explicitly the original reference frame. That could be something like a faraway observer that was describing the setup in the lab. So the reference frame transformation operator that we have to apply is actually the same one that we had before. And using this we find that the superposition of the Earth is transferred into the superposition of the particle to make sure the relative distances are the same. And then here we can just solve the problem using known physics. Now you will have a particular quantum state that describes the initial positions of the particle, and based on that you can now either apply Newtonian gravity, or if you want to make it more general for arbitrary gravitational fields, you can use the geodesic motion, assume the particle moves kind of along semi-classical paths. This is of course idealizing away a bit the spread of the wave function. And we know from the experiments that the particles are actually going to pick up a quantum phase as well, and that will depend on the path that it's falling on. But in any case, in the new reference frame, we can easily time evolve the quantum state, find that the particle falls in the superposition, and then on that time evolved quantum state, we just apply the inverse of the quantum reference frame transformation that we derived earlier. And this will give us the quantum state at any time in the original reference frame. And importantly, of course, this relies on the assumption that the laws of motion are actually invariant under this transformation. So it relies on this extended symmetry principle or quantum symmetry principle. Maybe a slightly different way to depict this is that we can actually circumvent assuming anything about the gravitational field of a massive configuration in superposition by just taking this little detour. So we go into the reference frame, do the time evolution there, and go back. However, we could also now say, well, actually, we would have arrived at the same solution if we had gone from here to here directly by just assuming that the gravitational field was in a superposition. We would have equally found that the particle moves along a superposition of geodesics, one determined by the gravitational field of this part and one by the gravitational field of this part. So one could, if one stretches the argument a little bit, see this as an independent argument for the quantum nature of the gravitational field, for at least these particular massive objects in a superposition. And it's one that relies on very few assumptions. Really, the only assumption is that that these two arrows are equivalent and that we have this quantum symmetry principle. Right. So I hope this makes clear the case for the quantum symmetry principles for the case of the translation group. I think if you have questions, now would be a good time because we're abstracting from here. Yeah?
Can you go back to the slide before?
Mm-hmm.
So in the case of the superposition of the Earth, where... Okay, go to the second picture there, right? With the superposition of the particle, and we switch to the reference frame of the Earth.
Yeah.
These two superposed particles, do they interact with the gravitational field as if they were, like as if they were entire whole particles? So it's just one particle that has two superposed states.
Yeah.
Can we just ignore it and say, okay, I'm just going to look at this one and assume that it's completely localized here, and then see how that moves? Is that how it works?
Right, this is the idealization that we're making. So it's kind of like if you have a beam splitter where you assume that each part of the beam follows its own well-defined path. I mean, over longer length scales, you would also have to take into account the spreading of the wave function, but if you just consider short enough length scales, it's basically two separate paths of the particle.
But we don't take into account the mass of the particles?
Right, only in the way it falls, not in the way that it back reacts on the gravitational field. This is actually very important. Like, we're not considering that the particle itself sources a gravitational field.
Okay, so we're just thinking it's massless or something?
Or a light test particle.
Light test particle, okay.
Yeah.
Thanks.
Yeah?
So here you have two systems, right? One is the test mass and the other is the Earth, right? And so you shift between these two systems, so to speak, where the superposition lies. Would you also go so far to say that you can actually shift between the system and the environment where the superposition lies? So, I mean, because typically you would think that not just the Earth, but also everything else is, so to to be classical around it. And then there is
Right.
some quantum particle with certain characteristic time scale before it becomes classical as well. So isn't it basically rather, in practice, that I would have to say, yeah, I'm shifting from seeing relative to environment a particle superposition, I'm seeing now, relative to the concrete test mass, the whole environment superposition, right?
Yeah. I mean, if you include everything in the description, everything is going to be in superposition.
Right.
Of course, this is practically very impractical. So the hope is that you can really maybe isolate your system in such a way, like make sure that all the other objects, like also for this case here, I mean, if we go into the reference frame of the Earth, like the lab is going to be in a superposition, but then you just have to make sure that the lab doesn't have any effects on the physics in either of the two reference frames. So for example, by making sure it has the same gravitational field in both of the branches so that you can ignore it. But technically, you're right, everything will be in
this case, then it somehow becomes interpretation dependent, right? Whether this is actually a physical move to switch references like this or not.
Yes. Yeah, I'm actually not sure if I would call it a physical move. It's kind of like if you want to jump into the reference frame of a particle that's moving almost at the speed of light, like how physical would that be? Like in the train, you can still think of setting up your measurement apparatuses and actually performing the experiment in the train. But at some point, as you go more abstract, it becomes more difficult to think of it as really a physical change.
Because it looks to me as if the scenario is, so to speak, on par, right? But to speak, I guess, depending on the interpretation of one case you have, you could say actually one reference frame is, so to speak, preferred over the other one, right? So you could say the classicalized environment system is preferred over the which some superposition is preferred. Or
I'm not sure I would go that far, that one is preferred over the other.
Okay. Yeah,
because if you include the interaction with the environment, also the particle in superposition will decohere at some point. So I think then it becomes a matter of which effects you model, and then you to do it in both frames.
Yeah, I'm just wondering because in some interpretation you won't even have microscopic superpositions.
Yes. Okay. Yes. And these interpretations, they don't agree with the symmetry principle.
Yeah.
These have a preferred reference frame.
Yeah. Sorry, I will ask.
All right.
Follow up on my question before. Is there a way to take into account the mass of the particles if we're saying like we're looking at like a mass or like my English is not great. Another massive object that's falling towards Earth that's also in this position. What would then can we look at say anything about this at this point?
Right. So just using the symmetry, then you're probably in general not going to be able to find a frame of reference where all the gravitating objects are definite. So in that case, you can of course still perform the reference frame transformation, but it doesn't allow you to make the step of saying, oh, now I can just solve it without making any assumptions about the gravitational field in superposition.
Okay, thank you.
All right. If everyone is happy with the translation group example, we can move on to the general idea. So actually there has been a lot of different examples from the one that I gave you now. There's been work on extending the quantum reference frames to the Galilei group, to spin rotations where you can jump into a particle with a particular spin, conformal transformations, Lorentz boosts, asymptotic symmetries at the boundary of space-time, and most recently also quantum diffeomorphisms. And instead of going through all these examples, which all have rather different technical frameworks, we're wondering if we can combine them in a common idea and a common framework. And really the idea behind all of these approaches is the same. We take the symmetries of our known physical theories, be it the translation group, the diffeomorphism groups, or so on, and we combine it with the linearity of quantum theory, which allows us to consider superpositions of the group transformations. And in this way, we end up with the extended symmetry principle based on two very basic principles of our existing physical theories. Like the symmetries are super important in studying classical systems, and the linearity of quantum theory is not just a feature of quantum mechanics, but it's a feature that continues on to quantum field theory. So So these are really crucial principles, and combining them already gives us a very useful tool to make predictions about situations in quantum gravity. So in this sense, it's really a first principles approach to quantum gravity, what we're trying to do here. So if we combine the two, we just end up with an invariance under quantum superpositions of the group transformations instead of classical symmetry group transformations. And recently, and this is now all non-published work so far, so I'm very happy to hear your thoughts on that. We've been thinking about how to depict these quantum reference frame transformations in a common framework. And we actually came across a very useful framework for this in the philosophical literature, in the space of models by Enrique Gomez and also in collaboration with Jeremy Butterfield. And they're studying symmetries in gauge theory and gravity by depicting them in the space of models. And the space of models really is just the space of all the possible configurations of a particular theory or solutions to a particular theory. Like if we have general relativity, a particular model would be a concrete solution to Einstein's equation, some manifold with some metric and matter fields on top. And each of these models is like a point in the space of models. And now if we have some symmetry group G, like the diffeomorphism group, we can partition the space of model into orbits. I don't know if you're all familiar with the term of orbit, but it's basically just given an orbit, all the elements on the orbit are related by the group transformation. And in this way, if we say it's really a symmetry group, we would say that two systems that are related by a group transformation, like two spacetimes related by a diffeomorphism, we usually take them to represent the same state of the world. So we can see these orbits as all representing the same physical state of the world, but just given in a different description. And this space of model actually really nicely illustrates the difference between the quantum reference frame transformations and the classical reference frame transformations. And the way that these reference frames come into the space of models is by considering sections through the space of models. So this is also still in the work of Gomez and Butterfield. They say, well, we have this huge representational redundancy in the space of models, and if we actually want to represent each possible state of the world by one unique model, we can do so by picking a section. So we're just, for each of the possible physical states, we're picking one model. And the way we pick this section is really just a matter of convention. This is why they call it a representational convention. A priori, that there is nothing that tells us whether we should pick this section or any other way of slicing through the space of models. And this section is what can also be seen as a choice of reference frame. So if we go back to the example that we saw before, we can now implement this in the space of models. We had the theory that could be Newton's theory of a gravitating particle in the simplest case, which is invariant under the translation group. A model could be, in the simplest case, be just the two particles, like the particle being on the left-hand side of the Earth or the particle being on the right-hand side of the Earth. In 1D, we cannot map them into each other by a translation, so they really represent physically distinct states of the world. But if we just took the particle and the Earth and shifted it over here, that would still be the same physical model. And what we do when we consider a classical reference frame transformation is that we do such a shifting, and we do this shifting completely independently of the particular configuration that we have. So for each possible state of the world, we're implementing the same translation, say by A. Now, this, however, only gives us a very small subset of the possible representational conventions that we have in the space of model. Particularly, we could choose anything that is slightly tilted. There is nothing that would say this is preferred over this one, and we would go from here to here by applying a different group element for each possible world. More generally, we could even take any squiggly line throughout the space of models, where now, to go from here to here, we apply a model-dependent group transformation. So that first checks what is the configuration and then shifts by a different amount. And this already sounds very much like the quantum reference frame transformations. We just have to make one important conceptual step, and that is that here we have the space of possible worlds, but they're all living like distinctly and independently from one another. Now in quantum mechanics, we can actually consider superpositions of those. And now if we imagine we actually have a superposition of a model here and a model here, then we can think of these orbits, roughly speaking, as branches of the superposition. And this brings us to the quantum reference frame transformation, where in our example before, for example, we had a superposition of the particle, of the Earth being to the right of the particle and to the left of the particle. And we started out with a particular representational convention where we chose to put the particle, say, in the 0 point of the coordinate system. And then, in order to change into the reference frame where the Earth is in the 0 point of the coordinate system, we had to apply a different translation in each of the two branches. So in the first branch, we have to shift everything to the left by some group element A, and then we have to shift everything to the right with the inverse of the group element in the other branch. So what the quantum reference frame transformation does, and the translation group is actually really nice in this picture because we can really think of the group being represented on the line. So the distance between the models here can actually be seen as the group element as well. So in this context, we can really think of the quantum reference frame transformation as shifting and kind of tilting the section and not just shifting it like the classical one. Of course, more generally, if we have a superposition of more different configurations, we can do the same wiggly line thing that we saw before. Now, the nice thing that I find about this representation is that it kind of makes this reference frame dependence of the superposition quite intuitive. Because one thing that the representational convention allows us to do is it kind of gives us a preferred way to put the two worlds together. So the issue is if we just think of the branches separately, there is actually nothing that tells us whether one point here is the same as a point over there. And if we pick a reference frame, then there is sort of a preferred notion of putting the two together. Namely, we should make sure that the reference frame is at the same point in the end result. So if we chose the reference frame where the particle is in the point 0, we're going to put them together at the point of the particle. Naturally, the Earth is going to be in a superposition of being left and right. And similarly, if we put the reference frame where the Earth is, well, that tells us that we should identify the point where the Earth is across the different branches. And then the particle is going to be either to the left or to the right, so in a superposition. So in this sense, it's maybe not so surprising that superposition becomes a reference frame dependent feature. And I also find that the way of thinking about this in the space of models makes it much more natural to consider these more general transformations. Because why should there be a preferred way of slicing through the space of models in a straight line? Like, what is the reason for doing that? So with this picture in mind, we can make a little bit more precise this idea of extended symmetry principles. We start with a known physical theory with a symmetry group G. We can say that models are physically equivalent if they're related by an action of G, if they live on the same orbit. And we already start with this invariance under the classical reference frame changes, like the constant shifts are already there in our existing physical theories. And then the linearity of quantum theory adds this additional step where we say, oh, now it's not just different possible worlds, but we can actually consider superpositions of different possible worlds. And then, of course, it also allows us to consider different transformations for each model or for each branch. And this way, we get much more freedom in representing the same physical situation, and we find that superposition is a frame-dependent feature. Again, if there is questions, there is a good point here to ask. Okay, that's good. Right, so now that we have set up the space of models, really any quantum reference frame transformation is going to look pretty similar. And we can very straightforwardly go to the quantum diffeomorphism straight away. We just replaced the theory of the Newtonian particle by GR. Our models are now really space-time configurations with some matter fields on top. They're denoted by chi here. And the relevant symmetry group is now the diffeomorphism group. So any two models on one orbit are going to be related by a diffeomorphism. And again, we can pick arbitrary sections through the space of models, where we just pick one particular representation for each space-time configuration. And ignoring any possible differences between coordinate covariance and diffeomorphism invariance, one can really see this as choosing a different coordinate system in each branch. I should add here that I've put different in scare quotes because it's actually really hard to make sense of how to say something is different or the same across the different possible worlds, and we're going to talk about this at the end. But intuitively speaking, you just arbitrarily pick your coordinate system depending on the configuration. And then again, we can really choose any slicing of the space of models that we like, and most generally, two such sections will be related not by a constant classical diffeomorphism, but by a quantum diffeomorphism, so one that acts differently in each orbit, or in the quantum level, each branch of the superposition. A different way to depict exactly the same situation would be to think of really these space-time manifolds in superposition, where these are the two different branches, and then we're just applying a different diffeomorphism phi 1 to obtain a new space-time configuration on the right-hand side, and a other diffeomorphism phi 2. And so we end up with a superposition of two rather different configurations. And now, the really interesting conceptual question is if there's anything new that comes from these quantum diffeomorphisms. Like the classical diffeomorphisms have initiated a lot of debate on the meaning of space-time, and it seems like we learned a lot from the classical diffeomorphism invariance and the classical Hall argument about the nature of space-time. So if we now consider a theory that is invariant under these quantum diffeomorphisms, is there anything new? Are there any new implications from the invariance under quantum diffeomorphisms that we didn't have under the classical diffeomorphisms? And there has been some work on this. I also learned last week that there is also some work in your group on this topic that suggests that one important object or feature of the theory that may be affected by quantum diffeomorphisms is the identification of points across the different worlds. So the hope would be that we can make something like a quantum Hall argument regarding the identification of points. But before I try to make this argument, let me very briefly review a hugely simplified version of the classical Hall argument. I'm sure you're all much more experts on this topic than me. But basically, the classical Hall argument starts from the diffeomorphism of general relativity. We know that if a space-time M, GAB, and potential matter fields not depicted here is a solution of GR, so is the same space-time that we obtain by applying a diffeomorphism on it. We can now take a particular set of these two space-times which differ only inside a bounded region, the whole. And because they only differ inside that bounded region, they are compatible with the same initial conditions. And now we end up with this dilemma that if we take them to represent physically distinct possibilities, if we know the initial conditions at the slice below the hole, there is nothing that tells us whether it will evolve into this space-time or into this space-time. And then, of course, there are many different ways to respond to this, but one that also seems to be very prevalent in physics and the quantum gravity research is to say, well, they're not actually distinct possibilities. They're just represented in different ways, but actually they're the same. And then we don't have this underdetermination anymore. However, this also implies that the things that look different in these two spacetimes, like whether the metric field has a certain value at a given point, should be taken the same. And one way to explain this is to say that the spacetime points themselves have no physical meaning, no ontological meaning. I'm sure there are many different ways to spell this out. So if we now go to the quantum level, is there something else besides the space-time points that loses its meaning in a similar sense, provided that we agree with the whole argument? And this thing is something like an identification map across the different possible worlds, or a counterpart relation between points across the different worlds. So when considering a superposition of such two spacetimes, there's a priori nothing that tells us whether 2 points are the same or different in the two branches. Like if we want to be able to say something like point P corresponds to point Q across the different branches, we need additional structure. Mathematically, this additional structure, which is given by some bijective map that uniquely associates a point Q to every point P in M1. And this is something that has been considered, for example, by Lucien Hardy in his work on quantum coordinates, but it also seems kind of arbitrary, right? What tells you which identification map to pick? So we were thinking if there's a way to motivate the identification map a little bit more physically. And one way that is based on some ideas of Westman and Sonego is to say, well, we should identify the points where the matter fields look the same. Like if I have a point P in M1 where my matter field is super peaked, then I should identify this with the point Q in M2 where the matter field is also super peaked. So we should identify points at which the fields, the matter fields, take the same values. So we're kind of materializing the identification map in a way. Of course, this is not the only way. It's just one that we found reasonable. And it's one that also fits kind of with the identification that we had in the previous examples, where we were either identifying the point in which the particle is or the point at which the Earth is. The only issue is that choosing one point particle is not going to fix the identification for an entire field theory. So this is like the generalization thereof. And now, as you may expect, given the buildup of the talk, we can actually check if this identification map changes under quantum diffeomorphism. So maybe just to say very quickly, it's actually very easy to build this identification map because either of the two fields in the branches chi1 and chi2, which can be seen as different field configurations in a superposition, both of them can be seen just as a map from the manifold M1 to the reals or from the manifold M2 to the reals. And if we say we identify 2 points if they agree with the field values, well, we just take the field in the upper branch, find that it has some fixed set of values C, and then we find the point which corresponds to that by taking the inverse of the second field. So the identification map will just be the composition of chi1 and the inverse of chi2. And now we can apply to this a quantum diffeomorphism. So we apply some diffeomorphism phi1 here, some diffeomorphism phi2 over here, and we find that both the matter fields and therefore also the identification map changes. I want to stress one point that was actually quite surprising to us, is that it not only changes under quantum diffeomorphisms where phi1 and phi2 are different, it already changes if we apply the same diffeomorphism in each branch. And the reason is basically that if we have different fields, applying a diffeomorphism will warp them differently in each branch. So kind of warping them relative to each other, although of course making sense of this concretely would require the identification map. Right, so with this, we can now try to make a similar variant of the whole argument with the identification map. Again, I realized last week that a very similar argument has been made before, just with a different kind of identification map. But if we now assume that whatever theory of quantum gravity we have, we don't care what it looks like, except that it's invariant under quantum diffeomorphisms, then if we have a superposition of spacetimes, I different version of a spacetime with a metric and matter field on top of it, if that is the solution of the theory, then so will be the solution obtained by applying a different diffeomorphism in each branch. Then, of course, we can still make the classical whole argument arguing against the ontological nature of the spacetime points and spacetime regions, but we also find that the identification of points across the different branches, even when we try to realize them through physical fields, becomes a mere matter of convention. And this is particularly interesting in the quantum context because it also means that superposition becomes reference frame dependent. Like if we want to say an event is localized or its location is in a superposition, what that means is its location is at 2 different points in the different branches. But what does it mean it's at 2 different points? Well, that depends on the identification map. And if that changes, also it changes whether it's in a superposition or not. And there are actually some interesting implications of this, for example, for indefinite causal order, where one can use this relativity of the superposition of locations to connect different variants of realizing indefinite causal order. But if you're interested in that, I'm happy to talk about this another time. I think for now, this is all that I would like to discuss with you. As you can see, this is all still under construction, so I'd be very happy to hear your thoughts. I think you all have much more background on the whole argument, so that should be very interesting. Just want to close by summarizing before we go into the discussion. So we heard about the formalism of quantum reference frames, in particular in the context of the translation group, and how that can help us to study problems at the intersection of quantum physics and gravity by taking a new perspective. And we also saw that in the space of models, we can see a choice of a quantum reference frame as an arbitrary section through the space of models, which differs from the classical reference frame transformations in that it doesn't just shift the section, but tilts and generally warps it. I mentioned that we use these extended symmetry principles as guiding principles, and that they can be seen as coming from a combination of two principles of our known theories, namely the symmetries of the classical theories plus the linearity of quantum theory, and how these render superposition a frame-dependent feature. And finally, we talked about quantum diffeomorphisms as a generalization of the classical diffeomorphisms to superpositions of spacetimes, and how these can change the identification of points across the different branches, and thereby makes the whole idea of identifying points frame-dependent and thereby maybe not metaphysically relevant quantity. So I have a bunch of open questions that I would like to discuss with you. One is how one can actually make sense of this identification across different branches of a superposition. And in particular, like in all of this, in drawing the pictures and in talking about different branches, it's all employing very much a many worlds-like language. But I would be very interested if one can make sense of all of this with a different interpretation as well, or if we're implicitly somehow already committing to many worlds in thinking about these things this way. And then something that we definitely want to work on, and that will be super important to make this really properly quantum, is how to model quantum phases in the space of models, and then how we can use this to study interference between the different branches in this framework. And I just want to close by thanking the Blaumann Foundation, who has kindly sponsored this visit, and you for your attention. Thank you.
Thank you very much, Marcel.
Thank you very much for the talk. Does the whole reasoning also on quantum diffeomorphism also work when you consider matter-free spacetimes?
Matter-free space?
Yeah, so spacetime only purely rational solutions.
Right.
And because you mentioned the word by Westman, but this is
yeah.
a very old idea. This is the idea by Bergman and Kovar and these people.
Yes. Yes.
So the idea is of defining a coordination, free coordination, physical coordination for space-time points in certain spacetimes, perhaps not too many symmetries, using the line tensor, for instance. And then when you apply all this to these configurations, what happens?
I think you can still do it without matter. You're just going to have to redefine the identification map using some gravitational fields.
But then what's the intuition? Because you said that the identification map will change.
Right, I think it should still probably change. So one idea would be, instead of, we haven't done the calculations, but if you don't have any matter fields lying around, what you could still try is to take some metric degrees of freedom and say you identify the points at which those coincide. I think the Kommer variables, there are some variables based on the Riemann curvature that could also be used to identify. And I would naively expect the same argument to still hold, because the metric is also just a field on the space-time, so to speak.
And you consider a superposition of the metric in the end?
Yes, yes. I mean, in general, these space-times differ in both the metric and the matter content.
Yeah.
Yeah.
Thank you.
Yeah, thank you very much. Can we go back to the beginning, where there is some argument about what the translation symmetry shows about quantum superposition. You know what I mean? So there's something suggested at least from the.
Yeah, I think. This one? No. Or in the space of models, or in the previous part? Not this one.
I think pretty early.
Okay.
Earlier, that you say this is also an argument about that the Earth is in superposition, or that gravity is in superposition, something like this to this effect. Do you know what I mean?
Well, the one with the four.
Yes. Okay. Now we have to watch all the animations again because there is unfortunately no way to skip this.
Well, look here.
Thank you. Almost done. This one.
The independent argument for the quantum nature of the gravitational field solved by massive object superposition.
Yeah.
So I'm wondering, I mean, the difficulty of saying that gravity is quantum is to actually isolate the gravitational system, right?
Right. Which is here assumed already in a way.
Exactly. And so in that sense, you might say it's not such a strong argument, right?
I agree that it's not a deductive argument. It's more like we notice we get the same predictions as if we had assumed that the gravitational field was in a superposition. Maybe that's a hint that we should treat it as a superposition.
Yeah, I just think it's a bit like buying too much into the formalism, because if you really believe that something is classical, but nevertheless coupled to something quantum, and then however forget a bit for the moment that the thing you put in on one side is classical, apply the transformations, then of course you can even argue for the thing you firmly know is actually classical, but it will be in superposition relative to some other system, right? I mean,
I'm not sure I understand.
I mean, say if we don't know whether the gravitational field is quantum or classical, right? It's of course equally likely. Then we basically have a Hilbert space, I guess, for the gravitational degrees of freedoms, and a Hilbert space for other degrees of freedoms, right?
Right, but we don't need this here. There is no Hilbert space of the gravitational field at all. We just don't talk about the gravitational field unless we're in this frame.
Okay,
This is why I'm saying also it's not a deductive argument for the gravitational field actually being in a superposition. It's more we find these predictions from this argument saying nothing about the nature of the gravitational field in this frame, and it coincides with predictions for a particular theory. Of course, for the quantum diffeomorphisms, you have to put in the assumption already that the gravitational field is in superposition.
So right now it's on Earth with some particle being in superposition, and I guess the particle is just subject to the potential of the Earth, and you could model this, however, also in a geometric fashion. So you say the particle is subject to I see. Okay. How would you do that? One particle. Okay, I will think more about this and then come back.
I mean, formally, it's really just like the three particles that we saw before. There is no additional Hilbert space for anything else. It's just the position of all the objects involved. Yeah.
Are there other questions? Yes, there are other questions, but that was a finger, right?
Yeah, maybe very quickly on this. What you just said, and related to the question about the interpretation of quantum mechanics and how to frame this. So, in this context, the idea is that you would maybe apply, because Neil's question, the one before, was that this whole thing makes sense only within the framework of mechanics where you can have superposition of massive objects. But now, from what you just said, it seems that in this context you may want to apply your privileged interpretation of or quantum theory in the end only to the particle, or would you need to apply it also to the Earth as a quantum system?
I mean, we're assuming that the Earth is also a quantum particle that is just prepared in a superposition. I mean, as I said in the beginning, it's not going to be the Earth. It's going to be some tiny gold sphere. but that should also ultimately be modeled by quantum mechanics. So it should have some position state that describes it as a quantum mechanical particle. Of course, if it is impossible to create a massive superposition, this argument is completely irrelevant because it wants to know what happens if we have a massive superposition. It does, however, show that approaches which say that massive superposition is impossible, that these must assume a preferred reference frame, because they would say this is possible and this is not possible. I don't know if that answers your question.
Thank you, Liz.
Okay.
Maria.
Yes, so I have a comment on one of your questions was whether it's possible to do this without having many possible worlds.
Mm-hmm.
And it seems to me that one way to go would be to talk about taking indeterminacy seriously. So instead of having many different worlds where you have definite properties in each of them, and there's the superposition of these different worlds with definite properties. One way would be to say you have one world, but we really take it seriously that the location is indeterminate within that world. And there are different kinds of metaphysical frameworks to work with this. This is also something we very briefly touched last week, but I'd like to discuss that more with you if you...
That would be super interesting. But then
Sorry,
just to follow up on that, would you then say that the transformation just acts on the indeterminate degrees of freedom rather than the entire world?
So that's the question that we're very interested in looking at, looking at the details. But I think that would be one way of doing it. So my supervisor Claudio, who unfortunately isn't here, he has a degree where he looks at having, for instance, the superposition of the particles, and you have it is indefinite because there are two different positions that are instantiated to different degrees. So I guess you couldn't talk about different branches throughout these different degrees. That would be one way of doing it. I'm looking at something a little bit differently, but that would be one way. Taking the indeterminacy seriously would keep it within one world, but then the question is how the details of that formalism would look like.
Very cool, yeah. Let's talk about this more.
Yeah,
Thanks.
absolutely.
I have a question. So you wrote or suggested on a later slide, which may not be necessary to pull up, a superposition of two different geometries or spacetimes, like ordered pairs of four-dimensional differentiable manifolds, metric field on them. So M1 G1 plus M2 G2.
Yeah.
And to me, that's not a priori a well-defined mathematical operation.
Yeah.
So is it just meant as sort of a label for, once we have a quantum theory of gravity, we will know that there will be sort of superpositions of a kind like that, and we will have a mathematical framework in which to make this precise? Or is there already some suggestion that there exists such a mathematical formalism?
I think there's two ways to answer this. I think for very simple configurations, one could maybe even use this kind of argument and then try to see this as a motivation to make it more mathematically precise. But in general, I agree. The idea would be whatever theory of quantum gravity is, let's assume it not only gives the semi-classical spacetimes in some limit, but that it still retains the linearity of quantum theory so that we can also consider superpositions of these. What the exact mathematical framework in the Hilbert space would look like for the metric is, of course, then very dependent on the quantity. And this is also why we found this space of models quite nice, because it allows us to talk about these things without necessarily having to put them in cats.
Yes. Thank you. Marta, did you have a...
Yeah, I had a finger on Maria's.
Okay, sorry that I jumped in.
So, like, your problem with many words is like that it seems to be the best fit for like representing the space of models, or it's more about.
I mean, it's not necessarily a problem. I think if you're predisposed towards many vaults, this is great because it seems to fit this discussion very well. I just personally would like to have an alternative as well to think about these things.
But so the origin is that you're looking into the space of models, or is something else? Or like this fact that you, like the interpretation that you give to the space of model, the fact that you call it like branches and...
Yes, but I think it would also arise without the space of models simply by speaking about the branches. It's already kind of suggestive. Like even if we skip this, if we say, oh, we perform a different transformation in each branch, this is already, I mean, I would be very happy if I'm sure there is a way to make sense of this. It's just that personally I haven't been able to make sense.
Yes, yeah. I mean, if you put it in that way, it seems more like a terminological method almost. Like, well, not all of the interpretation are fine with having like superpositions like as branches, but maybe you can, find some other way, like, I don't know, speaking in fictionalist terms or something like this.
Yeah.
So,
I mean, this is also why I came here, to hear the different possible ways. So,
no, but it's interesting.
I was wondering if just the symmetry principle that the laws are invariant under these quantum diffeomorphisms, if that already sort of whittles down the interpretations to many worlds, because I don't think collapse theories would be able to.
Right. Collapse theories are ruled out by Fiat because they don't respect the symmetry principle.
Right. Okay.
Yeah.
And then for Bohmians, because the superpositions are epistemic, and they also require preferred foliation, they would be ruled out as well.
Okay, I haven't thought about that yet, but if you understand this, I would be very curious to.
That's my first shot at just trying to compare what the different interpretations would require. And so to me, it does seem like, other than the language, just the constraint of invariance already predisposes you to many worlds. Or something like what Maria suggested if you don't have collapse.
All right, very interesting.
So that's a finger. Just quickly on the motion. This is a very interesting question to explore. On the one hand, I guess you could say that Booleans have a privileged reference anyway. But on the other hand, maybe you can run these kind of arguments purely at the level of the wave function.
Right.
Because there is this story of surrealistic trajectories in Boolean mechanics anyway. So maybe you can build something at this level.
Right.
And then you have to get, of course, superpositions and everything. So.
Yeah, I mean, you don't have to take it as real. I mean, you can just see it as different ways of writing something that is fundamentally a particle, and maybe still have on the representational level the invariance.
Well, just a slight finger on that first, just to say that.
Slight finger. That's
I mean, it doesn't require a response. It's just like a note. But there's been some papers that suggest that not all of the mass in Bohmian mechanics can actually be tied up with the particles. So if the mass is really distributed with the particles, then it may not look that different between the Bohmian and Everettian pictures.
Very interesting.
I can send you references.
Yeah, please.
But my real question was, I don't know if you've had a chance to read any of like Wallace and Timpson's work on ontology for Everettian pictures, but it seems like they're kind of leading ontology in the 4D world for Everettian multiverse, interpretation of quantum mechanics is the space-time state realism picture, where like everything becomes a function of space-time state, which it seems like really privileges the idea of space-time state points, because it's those points that, far from being physically insignificant, have the state, which is the real, ontology of the system. So I guess I'm interested if you haven't read that, no worries. If you have read that, I'm interested in what you think of how this argument would play with that kind of ontology.
Yeah, I think I don't quite know what you mean by a space-time state point, but maybe we can discuss this later if you send me the references. Cool.
Yes.
Yeah, so coming back to the
Yeah.
different arguments.
Yeah.
I think the way I was trying to think of it was
think of the Earth as having to be replaced by the G, say the metric, right?
Mm-hmm.
So basically, yeah, you have the metric, which is determinate, and then you have these two particles of position, right?
Right.
And then I guess the independent argument for condemnation of gravitational field sourced by massive object position is supposed to be, well, now we use a switch to the other reference system, right? And from that, it looks as if, yeah, the particle determinant and the metric is superposition, right? So what actually explicitly talks about the metric, right? Okay, I see. Yeah, and there again, okay, so this is the argument, I guess, right? Exactly. Yeah. There I would say it's really hinges on, of course, how much you think you can decouple the G from other degrees of freedom to do this, right? Or how you, yeah. So it's, yeah, I don't know. I'm not really convinced with the argument, but I think it's
no, me neither. Also, but yeah, I think it's not a bulletproof argument. Yeah. I think really, in the end, the idea is just to say we're kind of splitting arbitrarily into what we put in superposition and what not. And in particular, it's kind of arbitrary whether we say that something is localized in a delocalized gravitational field or if something is delocalized in a localized gravitational field. Like we can have these two situations, they give us exactly the same predictions. Maybe it doesn't make such a difference, and if it doesn't make a difference, if we have the one situation, we should also have the other situation. But I'm not claiming that this is really a deductive argument per se.
It's kind of secular, right? It's, I mean, depending on whether you think gravity can be superposition or not, you can do the switch or not, right? So in that sense, yeah, you don't get beyond that. So yeah, I don't know. We often like to do singularity charts.
Exactly. Yes, I have a figure on that. Yeah. It seems to me, as an argument, circular in exactly this way. But maybe we shouldn't think of it as an independent argument, but rather as like a coherence check.
Yes. Actually, to be honest, it used to say hint on previous slides, and then I was like, let's make a bolder claim. But I think actually it is more of a coherence thing.
So
it's not a full argument.
Presupposing, which is not independently somewhat establishing that this is the right way to go, but it is coherent. It can be made to fit in all these ways.
Yeah, and I think still, even if you don't care about the quantum nature of the gravitational field, I think at least the motion of the test particle, that is completely independent of whether you can put the gravitational field in superposition or not. Because for this you have to at no point speak of the gravitational field in the superposition. So I think there is one argument for the motion of the test particle, and then there is the extra step of trying to say, maybe this implies that there is a quantum nature. But yeah, I agree. The second step is just a coherence. It's coherent with having a gravitational field in superposition. Yeah.
I think I have more questions if you don't. That's just a small technical point that I noted. The problem with the quantum diffeomorphisms, or by taking. Vincent was already talking about that by sort of looking at the matter fields and see where they look the same, and identifying points. Sort of having a counterpart relation between the points based on that. And you've shown there's going to be some problems with that, but. There's going to be one technical challenge also in the case you have symmetries, in the sense of the space-time structure, the matter field distribution has some sort of, it's not a symmetry of the theory, but like a symmetry of the model or the situation.
Yeah.
To speak extremely, you can think of Minkowski space-time with a couple of constant scalar fields.
Of course, I completely agree. It only works.
You need to have a sufficiently varied or rich physics to be able to do that even.
Yeah, I completely agree. They need to be bijective, basically, because otherwise the identification map is not going to be bijective, and if you have symmetries, that is screwed up. The hope would just be that realistically we have a lot of different fields, and hopefully if we combine all these fields, maybe we can at least make sense for the things that we're interested in. Maybe there's a point in the universe where it's too symmetric, but then this is not something we need to worry about.
Yes, that's a reasonable expectation, because oftentimes these very high degrees of symmetries are really artifacts of some sort of idealization
Right.
that we're looking at. Yeah. If nobody has another question, then please join me in thanking Viktoria once again.